Okay, next paper.
Good morning, ladies and gentlemen. My name is 2019. I'm coming from National Formosa University of Taiwan. And today my topic is talking about the study on the implementation of multi-axis cutting and cyber-physical system on Unity 3D platform. And here's my outline. We first introduce our background and our research methods. Then we will introduce our program develop environment code Unity 3D. Then through the coding simulation to understand how we construct our model. Then the efficacy optimization shows the reason why we have to do the parallel algorithm to accelerate the system performance, then all the way down to the conclusion. So first we're talking about our research background. So why we choose 5-axis machine for our coding simulation system and why we wanted to combine it with AR/VR technology. Because 5-axis machining has been widely used in many aspects, such as aerospace, bioengineering, and the automobile. This industry requires high precision of complex surfaces, and the AR/VR technology has been widely used in recent years and has become probably the most popular applications in smart manufacturing. So here's our research method. We first obtain the NC code generated from the Hypermill. Then we use the Visual C# to develop a NC interpreter for head and hand. And then we convert those NC code into moving position. Once we got moving position, we can present the 5-axis processing in Unity 3D. Then in order to monitor our system in real time, so we have to do the parallel algorithm to do the simulation. And after this, we wanted to make it a cyber-physical system. So we first obtain each code position from head and hand ITNC 530 controller, then through the Remo2 SDK to integrate with our system. So at B chapter, we will introduce Unity 3D and machine movement simulation. So why we choose Unity 3D? Some of you probably seen this logo before. Unity 3D is supported by many platforms and community, such as ThemeVR and Vuforia and the SS Store. So in such convenient environment offered by it, we can spend more time concentrate on our programming. And now to the machine movement simulation. On the left-hand side of the picture is the machine that we use as a model inside our simulation system. It's called the Quasar UX300. And on the right-hand side of the picture shows the reason why we have to use the homogeneous transformation matrix to convert the coordinate system. Because while we only use the 3 axes of the 5 axis to do the processing, it will move according to the mechanical coordinate system. But this definition will be changed after the incline platform command is executed, which is the A and C axis. That means it will rotate. So we don't want that. We want the whole moving position is moving according to the mechanical coordinate system. So here's where we bring the homogeneous transformation matrix into the system. Because we wanted, so we have to use the homogeneous transformation matrix to convert the vector, to convert the coordinates of the vector back into mechanical coordinate system, so that machine can move correctly in the simulation system. And at the C chapter, I will talk about how we construct our solid model and how what kind of method that we use to determine whether the 2 objects are collide with each other. And then I will talk about enhanced surface precision. So before I tell you how we construct our solid model, we first have to look at the data structure. The data structure that we use is called the arc tree. So what is arc tree? Arc tree is a tree-like data structure, and this kind of data structure is good for rapid data searching. On this picture, it shows its data structure. Each octree contains 8 nodes, which on the top there's 4 nodes, and down there's 4 nodes, so there's total 8 nodes. And each node represents a 3-dimensional region. And this region are we so-called the voxel. So I believe a lot of people have played a toy called the Lego in your childhood before. So the voxel is kind of like a Lego. And on the outer surface of the voxel is called the root. So now we know what octree is. Now we wanted to know how octree can help us while we construct our solid model. So here is a tool model. It's a top viewing. And here is a workpiece model. So when the tool model collides with the workpiece model, the algorithm will start to search those intersected voxels in the octree, then subdivide them into smaller voxels. By doing so, we can save more time on data searching, because every voxel contains vertices and triangle isosurface information, which will be mentioned later on. And at this page, we will talk about the collision detect and the APT tool. So in order to determine whether the two objects are colliding with each other in the simulation system, we will use the OBB. So what is OBB? OBB refers to oriented bounding box. So how does OBB work? We simply project two objects' bounding box projection to the detached axis, L. Then we will draw a perpendicular line to it called the detached line. And if this detached line can intersect with both objects' bounding box projection, that means two objects are colliding with each other. And in this research, we will use the double layer OBB in order to increase the kilolane amount of volume. So right here is the APT tool. So the reason that we use the APT tool is for rapidly determining whether the 8 nodes of the voxel are inside the tool. So we use the implicit equation to construct our APT tool. So I'm trying not to bore you with the formula. So this is the basic concept of the implicit equation. So if the equation is smaller than 0, means the point is inside the tool. Larger than 0 means the point is outside the tool. Equal to 0 means on the surface. And now at this page, we will talk about enhanced surface precision of workpiece. So when the tool model collides with the workpiece model, you will generate some sharp edge voxel around the tool. So like this. In order to fix this problem, we will use the Marching Cube algorithm. So what Marching Cube do is that it will focus on those sharp edge voxel to generate a series of triangle isosurface to mimic the contour surface of the workpiece after being cut. So after this, after we construct our triangle isosurface, there will be a gap between the rest of the workpiece and the triangle isosurface that we just built around the tool. So in order to fix this problem, we will use the Marching Square algorithm. So what Marching Square do is basically like a Marching Cube, but it's more like a 2D version. And now we're talking about the efficacy optimization. So in order to monitor our simulation system in real time, there must not having lagging problems. So we have to use the parallel computation to accelerate the system. Everything have to be fast so you can see it in real time. So when you're using multiple threads to share the resources, these threads we're trying to modify the shared content at the same time. And that will lead to inaccurate calculation results because there will be competition between the threads. So in order to avoid this problem, we have to equally distribute this information or resources to each thread. Then after we equally distribute them, then we will do the computation or the measure construction. And so here's another way to optimize our system. It's called the object pool. But before I talk about the object pool, we have to first look at the garbage collection, GC. So garbage collection is basically a memory recycle mechanism. It will accumulate a certain amount of useless data. So the useless data refers to when doing the cutting process, remove some material and those material is called the useless data. So anyway, when it accumulates a certain amount of useless data, it will remove them at the same time. And while it do so, it will drag down the system performance significantly. And in order to avoid this problem, we have to lower down the trigger frequency of the GC. So this is where we bring in the concept of the object pool into our system. So what object pool good at is that it's good at manage those frequently reused object and data. So we don't have to wait for the garbage collection to release the memory space. It could speed up our system process. So at the E chapter, we will show in our simulation process and cyber-physical system and show you how it works. And we will do a little comparison between before and after using parallel computation and parallel rendering. And we will show the result. We'll do the comparison using and not using object pool. So every procedure that you see in this video is following the actual procedure of 5-axis machining. Sorry, the subtitle is manual. So you can see the model starting to take shape. So now we know our kind of simulation is working well. Now we wanted to make it a cyber-physical system. So here is our remote monitor interface. And here's a simple model that we use to test after we combine it with the 5-axis machine. So notice that I can still change different perspectives during the process. It will not affect its mechanical coordinates. So this is the result in the simulation. And here's the result of the actual one. So now we're talking about the comparison between the parallel computation, before we use computation, parallel computation, and after we use the parallel computation. So after we use the parallel computation, we could increase the efficacy about 69%. And after we use the parallel rendering, we could increase the efficacy about 98%. And the results showing using and not using object pool, after we use in the object pool, we could increase the efficacy about 98%. So here's the conclusion. This study successfully established a 5-axis coding simulation system on Unity 3D. After a series of tests, parallel coding simulation can improve about 69% of performance, parallel rendering can improve about 98% of efficacy, and memory can improve about 98% of performance after optimization. Cyber-physical system is achieved by obtaining coordinates data through the Remote OS SDK and ITNC5 controller, which enable the system to achieve remote monitoring function. So here's all my report. Thank you for your listening.
Some question? What is the next step? What is the perspective of this optimization? Do you want to improve?
Because the
develop more.
Nowadays trend is the Industry 4.0. So everybody will trying to combine the AR VR with the actual machining process. Imagine that you have a lot of company in your hands and you are on a business trip and you wanted to know what's going on in my factory. All you have to do is put on the VR glasses to watch, to see what's happening in your company and to see how's everything going in your factory. So you can get the first-hand information. So that's our perspective to doing this research.
In a way, what is the difference between the computational time for simulation and the time for production in a common pieces?
You mean parallel computation and the actual
simulate
manufacturing time? Yes.
The production and the reality, between the reality and the simulation. There is no difference?
No difference, because we use the parallel algorithm to accelerate it, so everything will happen in instantly. So you can see it in real time. Thank you.
Okay, thank you.